Okay, this lesson is about damped oscillations. In the previous lesson, we looked at the oscillatory motion of a simple pendulum, and we also looked at the motion of a physical pendulum. In both of those motions, we treated them as ideal systems, and so the systems would oscillate indefinitely, and there would be no resistance to the oscillation of the objects involved. For example, there is no resistance to the oscillation of the simple mass pendulum, and there will be no resistance to the oscillation of our physical pendulum. So those were ideal systems. In a real system, there is actually damping involved, and the damping just means that there is a resistance to the oscillation, whether it's air resistance or if the object was oscillating in a liquid, then the resistance would be due to that the viscosity of the liquid. So if we consider, for example, that we have a mass that is oscillating at the end of a spring, and that mass is oscillating in a fluid, for example, water, we can write equations of motion to represent the motion of that mass in the fluid. So let's first consider a mass oscillating at the end of a spring, and we say the spring has spring constant. Suppose we place the mass in a fluid. So let's say we have a fluid like water. We'll place the mass in the water as it's oscillating, and so in this case, the oscillations will slowly decay and come to a stop. So the system is shown here where we have the mass at the end of a spring or spring constant K. So this mass is M, the spring has spring constant K, and we place it in a container of liquid, perhaps it's water. And so the system is going to oscillate back and forth in this liquid. Let's say that the liquid has a resistive force given by which depends on the velocity. So let's say a better way to say it is that let's say that the mass experiences a resistive force which is proportional to its velocity. So we can say that the resistive force R is equal to minus B times V. Of course, this is a vector quantity, so let's write it that way, where we can say B is a constant. It's a constant of proportionality, and it's called the damping coefficient. Now, because we also have a spring system, we have a restoring force equal to minus kx, according to Hooke's law, of course. So F is equal to the restoring force of the spring. So the resistive force in the fluid is the damping force. And you can also think of it as a retarding force. So let's a retarding force because it retards the motion of the mass at the end of the spring. Okay, so let's write our equation of motion. The net force is equal to mass multiplied by acceleration. That's Newton's second law. The external forces are the spring force minus kx, and the damping force or retarding force minus b times v, and this is along our x-axis. So let's say that our vertical direction now is x. We can do it along y if you like. Well, let me do it this way. Since we typically call the vertical scale the y-axis, I'll just use y. So minus ky equals minus bv in the y direction, and that will be equal to m times a in the y direction, acceleration along the y-axis. Okay, so the motion is in the vertical direction. So we can write minus ky minus b times dy dt equals m d squared y dt squared, that way. Now the solution to this differential equation is a lot more detailed, so we won't try to solve it. I will just quote for you a solution. So I'll just write that the solution of this equation requires math that we don't know at this point. So we will just quote the solution. As you go further, I'm sure you will learn how to solve this type of differential equation. So for now, the solution is given by y of t equals a certain constant a times the exponential function e raised to the power minus b over 2m times t, like that. And then we shall have cosine omega t plus phi. So this solution is basically like the previous solutions to any type of oscillatory motion. The only difference is that we have some extra term in front of the cosine omega t plus phi. The angular frequency of oscillation here is given by, let's write that down. And to simplify things, we can replace k over m by a certain frequency omega naught. So this is the omega naught, and this omega naught is basically the angular frequency that we got for the previous simple pendulum as well as the physical pendulum. So we can write the angular frequency to be equal to omega naught squared and minus b over 2m squared, like that. So let me make a quick correction. We are replacing k over m by omega naught squared. Okay, so that's what we have. So omega naught is equal to the square root of k over m. So this omega naught is called the natural frequency of the system. This would be the oscillation frequency if there was no damping. Now let's look at a few scenarios. So we'll consider a few cases and we'll try to keep it simple. So the first case, let's write it this way, case 1 is when you have b over 2m less than omega naught. So we are saying that the retarding force is small enough, or the resisting force is small enough that the b over 2m is less than the critical frequency. In this case, this is called an underdamped system, and we can say that the system slowly decays to a stop. If you plot a graph, it will look this way. So you think of the displacement or the amplitude as a function of time, and it starts off oscillating, but the oscillation slowly decays to 0. Let's look at another case. This is case number 2. Let's think of the case where B is critical, B subscript C. So we're thinking of a case where B reaches a critical value, B subscript C. And so we will have B subscript C over 2m equal to omega naught. So suppose we have the B subscript C over 2m equal to omega naught. This is called a critically damped system. Let's underline that, critically damped. So in this case, the system, when released, will just slowly approach its equilibrium position, but will not actually cross it. So if you drew a graph, it will look this way. So again, we have the amplitude as a function of time. And if you release it from equilibrium, it will just slowly approach equilibrium. And then the third case, we shall call an overdamped system. In this case, b over 2m is greater than the angular frequency or the critical frequency omega. This is called an overdamped system. In this case also, when the system is released, it will not oscillate, it will just slowly return to equilibrium. And if you drew a graph of that, amplitude versus time, again it will slowly just return to equilibrium. Now the last lesson on this is forced oscillations. So in this case, we can consider that we have a system that is oscillating. Perhaps it's in a damped state, but then we can apply a force to help it along. So we call it a forced oscillation. So instead of having an ideal situation where the system is oscillating freely like a simple pendulum or a physical pendulum, we can think of a damped oscillation system, but instead of letting it slowly decay, we can give it a force to help it along so that it oscillates with a periodic force. So we can say that in a forced system, rather than letting the oscillations decay, we can provide a periodic force to aid oscillation. So the force can be a force of the form F of t equals F naught sine omega t. So let's consider our previous damped oscillator. This time, let's add a force F of t. So the net force in this case, again, is equal to ma. That's our equation of motion. And so if we add a force F of t, then F of t is F naught sine omega t, and we shall now combine it with the retarding force B times V. Remember that we're working along the vertical axis, so we say V in the y direction minus the restoring force K in the y direction, and that should be equal to m d squared y dt squared. And we are just going to replace V in the y direction by dy dt. So we shall have F naught sine omega t minus B dy dt minus K times y equals m d squared y dt squared. So this is the equation of motion of a forced oscillatory system. Again, we will not solve this equation because the solution of this equation is outside of our scope. So this is outside of our current knowledge. So what we will do is just quote it. So we shall say then that x of t, sorry, not x, I'm working along y. So I'll say that y of t is equal to a cosine omega t plus phi. That's the general solution for oscillation for an oscillatory system. This is the same solution that we had for the motion of a particle in simple harmonic motion. I'm just doing it along the y-axis. So instead of x of t, I'm using y of t. The a in this formula is given by f naught over m. Divide that by the square root of omega squared minus omega naught squared all squared plus let's say b omega over m. Okay, again note that omega naught is the natural frequency and omega naught is given by the square root of k over m. That's our natural frequency. And natural frequency occurs when b is equal to 0. So we'll say that that's our natural frequency when b is equal to 0. When damping is small, the amplitude of oscillation is large when the driving frequency omega is near the natural frequency omega naught. So when this happens, when omega is approximately equal to omega naught, we have resonance. Resonance means the amplitudes become very large and the system is now resonating or oscillating at a very large amplitude. Draw a graph of amplitude versus frequency. You will see that at the critical frequency omega naught, you have a very large amplitude. And this will happen when b is equal to 0. There are other amplitudes also, so for very large b, you have a very small amplitude. So this will be when b is large, and for a relatively smaller b, you can have an amplitude that looks like that. And b equals 0 means you have resonance. So we'll stop here.